Alright, in this video we're going to be talking about stationary points, the types of stationary points, and how you can work out stationary points given the equation of a certain function. And in this video we're just going to be talking about how to work out stationary points. In another video I'll be talking about how we can work out the type of stationary point that we have. First off, what is a stationary point? I've been saying that quite a bit for the last 10 seconds. A stationary point is any point on a function, or specifically the graph of a function, where there is no rate of change. The graph is neither increasing nor is it decreasing at that point. And if we have a look at this graph that I've sketched over here, there are a few stationary points that I can recognize. I can recognize a stationary point over here, as well as over here. And what's so special about these stationary points, or these points in particular, is if I were to draw a tangent line to each of these points, you can notice that the tangent line is completely flat, i.e. the rate of change of the tangent line is simply 0. And that means that point is referred to as a stationary point because it's not moving up or down. Particularly, this point here would be referred to as a local maximum for obvious reasons, because it's going like a max. If we were to just zoom in on this part of the function here, we can see that it's like a maximum point. We can also have what's known as a local minimum. Because we can see, if we were to just zoom in on this graph, we can see it's minimum for this section of the graph here, almost like it's just bouncing back up. But we can obviously see for the entire function, there is a point much lower than our minimum over here. That's why we don't call it just a normal minimum. We would call this a local minimum. And the last stationary point I've identified on this function here is this one here. This one is called a horizontal point of inflection. What is a point of inflection? I'll do that in next video. So now continuing on from here, to work out the stationary point of any graph, of any function, doesn't have to be this one here, it could be any polynomial, any trigonometric, anything which you can differentiate, we can recognize the stationary point will always have a flat line, i.e. the derivative of that function will be equal to 0 at that point. And if the derivative of the function is equal to 0 at that point, we can simply work out the stationary point, more specifically the coordinates of the stationary point. So let's give a try at a few examples. The first one we're going to start off with is f of x equals to x cubed, take 12x. And the question I have is, what are the coordinates for the stationary point for this function here? Where are the stationary points and where do they occur? And first thing I would have to do is I would need to differentiate this function. So f dash x is equal to 3x squared minus 12. And we now have the derivative. We have recognized that if there is a stationary point, in order for there to be some sort of a stationary point, your derivative must be equal to 0. So all I'm going to do is I'm going to let the derivative function of my curve equal to 0. And all I'm going to do now is simply solve for the value of x. So to solve for x, we can say that 12 equals to 3x squared, hence x squared equals to 4. And my two values for x are either x equals to minus 2 or x equals to 2. So this is the x values at which my graph will be stationary. And what I need to work out now is where on my original curve, on this function here, what is the y value for which the stationary point occurs at. So I can work out both the values of f of 2 and f of minus 2. So f of 2 in this case would simply be 2 cubed minus 12 times 2. And that would be equal to 8 minus 24, which is equal to minus 16. So the coordinates for this function will simply be 2, minus 16. Now for f of minus 2, we can do the exact same thing. We can sub in minus 2 into the original function here, not the derivative function, but the original function, because we want to work out the coordinates. And in doing so, we get minus 8 plus 24, which is equal to positive 16. So our other coordinates are minus 2, comma 16. And that is where the graph for both of these functions will be completely stationary, completely flat. Let's have a go at another example. We're going to have a look at y equals x 3x to the power of 4, take 16x cubed, plus 24x squared, take 10. Where do all the stationary points for this equation occur at? Now, there is a little bit of cubic solving if some of you can foreshadow what's going on here, but I will walk your hand through this one here. To work out the stationary point, first thing we're going to do is we're going to differentiate. The derivative of this function is 12x cubed minus 16 times 3, because we have to bring the derivative to the front. So that's 48x cubed, x squared, plus 48x. And we can simplify this by factoring out a 12x, and we'll be left with x squared, take 4x plus 4. And what we can simply do now is we have a perfect square. We have a quadratic that is perfectly factorizable. And we can say this is the same thing as 12x. And if you're not sure how to factorize this by simply looking at it, I do have another video that will come up shortly on how to do this. But it would be x take 2 whole squared. And again, the question that I had was, where do the stationary points occur for this function? So what we have to do is we want to let the derivative of our graph equal to 0. So I'm going to let these two lines equal to 0. And all I'm going to do is simply solve. And to solve these two equations, we can use the null factor law. The null factor law says that if we have two functions that are multiplied to each other, and we want the entire equation to equal to 0, then either this function has to equal to 0, or this function has to equal to 0, because that's the only way two things multiplying together can equal 0. So either 12x is equal to 0, so either 12x equals to 0, in which case x is equal to 0, or we can say x take 2 is equal to 0, in which case x is simply equal to 2. So we have just worked out the x value for where our stationary points actually occur. Still not done, we need to work out the corresponding y values. So into the first one, I'm simply going to plug in when x equals to 0. So 3 times 0 to the power of 4. And you can recognize that all of these terms will be cancelling out, and we'll simply be left with minus 10. And when x equals to 2, we're going to do the same thing. So y equals to 3 times 2 to the 4. Take 16 times 2 to the 3, plus 24 times 2 to the 2, take 10. 2 to the 4 is 16, and 16 times 3 is 48. Minus 16 times 8, which is 96, plus 24 times 4, which is 96, minus away 10. So these two terms will cancel, and all we're left with is 38. So these are our two coordinates for which we have a stationary point. Let's continue going. I'd like to work out the stationary point for the following function. Y equals e to the power of 2x minus 2x. Pause the video and have a go yourself. Okay, that's enough time. Now what we're going to do is we're just going to differentiate, as always. Differentiate this function. What we'll get is 2e to the power of 2x, take away 2, And you can have a look at my differentiation series to see how we can differentiate e to the power of 2x. Now that we have this, we let this equal to 0. So that would be 2e to the power of 2x take 2 equals 0. And to solve this, we can simply factor out a 2. We can divide both sides by 2. So 0 equals e to the power of 2x take 1. And we can solve when 1 equals e to the power of 2x. And we know that anything where the x is in the exponent, we know a base raised to the power of 0 is the only thing that'll give us 1. So that would mean that 2x would have to equal to 0. And that means x is equal to 0. And now to work out the corresponding y value, all we have to do is substitute that back into the original function. So y value when x equals to 0 is simply e to the power of 2 times 0. Take away this. And that is simply equal to e to the power of anything 0 is always 1, minus away 0, which is just equal to 1. So our coordinates would be 0, 1. That is where the stationary point occurs for this function here. Let's keep going. Y equals x e to the power of x. To work out the derivative of this first, in the process of trying to work out the stationary point, what we're going to do is we're going to use the product rule. And to use the product rule, I have another video, so you can have a look at that, how to use the product rule. What we can do is we can differentiate the first function and keep the second. And then we can keep the first function and differentiate the second. So this would simply factor into e to the power of x times by 1 plus x. And because we're trying to work out stationary points, let this equal to 0. So we want to solve when does e to the power of x equal to 0 and when does 1 plus x equal to 0. In looking at this, there will be no real solutions for which e to the power of x equals 0. Because if we have a look at the sketch of e to the power of x, or any radical function for that matter, not radical, any exponential function for that matter, if we were to try and sketch this function out, we can recognize that there will be a horizontal asymptote at the line y equals 0, and there will be an intersection at the point 0, 1. And we can notice that this graph here will exponentially rise like this. And because of this asymptote at y equals 0, we know that e to the power of x can never equal to 0. And it can also never be any of these negative values down here. So that means for this one here, if I were to get rid of this graph, for this one here, there are no solutions. But there are definitely solutions for this one here. For 1 plus x, we can definitely solve this. X is simply equal to minus 1. And to work out the y value, you guessed it, plug it back into the original function. So the stationary point for this function here would be equal to y equals -1 times e to the power of -1. And that would simply be equal to -1 over e. So therefore your coordinates are simply -1 and -1 on e. Let's keep going. We're going to work out the stationary points for the function y equals 2x ln x. Again, this is the product rule. To work out the stationary points, we're first going to differentiate. And the derivative of this function would be differentiate the first function, keep the second, then you add it the opposite way around. You can do it either way around. I sometimes switch it up. We can do add, keep the first function, and times by the derivative of the second. In this case, the first function was 2x, the second was ln x. Oh, that was an accident. The first one was 2x, and the second one was ln x. So now in differentiating, we can say that this is equal to dy on dx. First off, we can say the derivative we want it to equal to 0. That's equal to 2 ln x plus 2. Now to solve this, divide both sides by by 2. So 0 equals to ln x plus 1. And now in solving this, we can say when does ln of x equal to negative 1? Now to cancel out the ln, we can simply raise both sides of our function to e. So that means e to the power of ln x is equal to e to the power of negative 1. And we know that e and ln simply cancel each other out. And now in doing so, we have x equals e to the power of negative 1, which equals to 1 over e. And to work out the value of y for which this statement is true, we plug it back into the original function. So y when x equals to 1 on e is 2 times 1 on e times by ln of 1 on e, which in other words inside here, I'm just going to write e to the negative 1. So here we will have 2 on e times by, and we know that ln and e here simply cross out. So that means we will have times negative 1. So our y value is equal to minus 2 divided by e. Therefore, the coordinates for which your stationary points of this function occur at will be at x equals to 1 on e and y equals to minus 2 on e. And that's how you find stationary points of any function.